Hello, everybody, and thank you for joining us. Today's webinar is on strategies to optimize the analysis of mercury in water and is being presented by David File. We will have questions and answers at the end of the webinar, so feel free to use the question and answer function. And I'm going to go ahead and turn it over to Dave now.
Okay, thank you, Shelley. Hopefully the sound's coming through okay, Shelley?
Yes.
Yes, I'm Dave File. I'm the product manager for Teledyne Leeman Labs. Just a little bit about myself. I have a chemistry degree from Northeastern University in Boston, Massachusetts. From 1971, I've been in this business a long time, 40 years, basically doing atomic spectroscopy. Over that period, I've done such things as manufacture hollow cathode lamps and designed graphite furnaces, hydride generators, and new AA systems. Most of that time was spent in research and development. So without further ado, I'll get straight to the topic at hand, which is really the determination of mercury in different types of waters. You have to start by going back to look at what you're really analyzing. Typically, waters, particularly the determination of mercury in waters, is a heavily regulated analysis. So you need to start by getting a good handle on who regulates the analysis, if there are specific methods that are required, what types of water you're allowed to analyze, the concentration ranges that are significant not only in terms of report limits, but also in terms of your typical concentration in your samples. And finally, which technologies are permitted by those methodologies if you are following a specific method. When you look at the EPA, which is typically the primary source for regulations of water monitoring, that is split up into several offices. The Office of Groundwater and Drinking Water really is enforcing the Safe Drinking Water Act. That's the driver for their operations. In the Office of Wastewater Management, that is actually handled by a different regulation, the Clean Water Act. These two offices, in many cases, work independently, have different methodologies that they require use of. The Office of Wetlands, Oceans, and Watersheds, they're just checking to make sure that both public and private water bodies meet the criteria for safe usage. And finally, the Office of Science and Technology is there to develop the methodology and to define the criteria of acceptable standards, etc., for both the Clean Water Act and the Safe Drinking Water Act. Pretty quickly on, when you start to decide on the types of analysis you're going to do, you have to look at whether you're going to do drinking water or wastewater management, wastewaters. The primary issue is the legal driver. They are different between the two water types, and the methodology that's required for the two types of water is different, and as a result, the technology involved for the determination of these two separate types of waters is different. So let's start with drinking water. Typically, for analytical methods and laboratory certification, drinking water requires that all public water systems have periodic monitoring to make sure that specific contaminants aren't present, and that includes mercury. Private wells that service less than 25 people don't fall under this Safe Drinking Water Act, but larger usage does. The methodology that it has to be used is very specific for drinking water, and we'll get into that on the next slide, I believe. And laboratories that are allowed to do this analysis need to be certified either by the federal EPA or by state EPAs. I should add here that in many cases the states have primacy, and the EPA methodology may be slightly modified by states for their specific certification requirements. For mercury, there are two levels that are important, the maximum contamination level and the maximum contaminant level goal. And for mercury, inorganic mercury, they are identical. They're both at 2 parts per billion. When you look at sources of contamination that can impact your water, there's numerous different locations, natural deposits, industry and refineries, runoffs from landfills and croplands. And of course the EPA purpose is to regulate the mercury in drinking water, and they recognize that health problems can be the result of amounts of mercury that are greater than the standard. This is just a indication of the mobility of mercury in the environment. It is easily transported from sources into other locations such as rivers and streams. Primary sources could be industry or natural occurrences such as volcanoes. Emissions get into the air. They can fall down as either a dry deposit onto land, or come down in precipitation, rain or snow. They can migrate from farms and other landfills, things like that, into the water. And once they reach the water, they can either be revolatilized into the air, or they can go into the sediment. And the third option is they can be absorbed by plankton and fish and bioaccumulated, and often converted to a more lethal species of mercury, a methyl mercury species. So when you look at the regulations for the drinking water regulations, they come from the CRF 40, Part 141, Code of Federal Regulations. And there are two methodologies that are allowed, either cold vapor atomic absorption, either manual or automated, or ICP mass spectrometry. There are no other allowed methodologies at this time. If you look at a summary of the method for 245.1, you have a known portion of sample of water, and it's digested. We'll get more into the digestion, heated with these digestion reagents to 95 degrees. And the end result is the mercury in the sample becomes mercuric ions. And those mercuric ions are then reduced with Stannous chloride, carried through an absorption cell, and detected by the technique cold vapor atomic absorption. The digestion in detail from the method itself requires strong acids, sulfuric, nitric acid, strong oxidizers such as potassium permanganate, potassium persulfate. Once those are added to your water sample, they're mixed and they're heated for 2 hours minimum at 95 degrees, allowed to cool. At that time, you do need to check to make sure that there's still an excess of oxidant present, and then before the analysis, you remove the excess oxidant using a hydroxylamine sodium chloride solution. These additions end up giving you about a 50% increase in the total volume of your solution. So there is some dilution involved. Most laboratories will handle the digestion, the heating phase, with something that's commercially available from a number of different sources, a hot block. Typically, these will have something like a carbon core and electronic heater to hold all of the sample solutions at 95 degrees for 2 hours. When you look at the actual analysis after the digestion in method 245.1, the original method was a manual system, and you can imagine that you have a solution that is your digestate, and you add stannous chloride to it, bubble through that solution, and the vapor that's produced is mercury at a 0 valence, and it's carried through a dryer into an absorption cell. And in the original cold vapor approach, that was part of an AA spectrometer. And once it reaches the absorption cell, it measures it as just a decrease in the intensity of the lamp in the AA itself. There are 3 different configurations for the manual system that are proposed in 245.1. Most of them dealing with the type of scrubber that you're using to remove the mercury at the end of the analysis. But the first one is a closed loop, and the others are continuous flow through the absorption cell. Well, this was a manual system, and very quickly it converted to an automated approach. It's fairly time-consuming and required operators to be present throughout the entire analysis. Today, most people do use a dedicated system or an automated system on an AA. The key differences with automated systems are that they use a peristaltic pump, such as this one here in the Hydra 2AA, to pump both their sample and their reducing agent, the stannous chloride, into a gas liquid separator. In the gas liquid separator, the liquid is pumped to waste, and the gas itself, including both the carrier gas and the mercury vapor, are carried up into the spectrometer. Typically, it'll have a dedicated mercury lamp and a detector that is located behind an interference filter, which is designed to limit the emission to the wavelength range of 253.7 nanometers. So this is typically a schematic of what an automated system will have. Typically, they will have a pump, and they will bring the sample and the reductant together in a mixing tube into a gas liquid separator. The gas generator will go through a dryer and then into the spectrometer. And this is indicated here by a lamp, absorption cell, and a detector. Today, there are some other options that are available where the sample and the reductant will actually be added to sample tubes, and that can eliminate the pump. That is an option for direct purging from the sample cup. That is available in several cases. for us, with the Hydra AA, we do have several benefits that people should be aware of. Typically, about 1 minute per sample is all that's required. We have a sensitivity with a detection limit of about 1 part per trillion. We have a pretty sophisticated gas-liquid separator that can handle difficult samples. We also offer overrange protection, which will eliminate long cleanups after a high unknown is introduced to the system. And we have a large capacity sampler so that it can handle a lot of samples without an operator being present. In terms of the actual throughput of the system, we typically can analyze a sample with uptake, rinse time, and analysis. The entire cycle will take about a minute, 71 seconds in this case, with 3 replicates. And we can achieve a detection limit with these system conditions of about 1 part per trillion. When we handle difficult samples, there are 3 problems that people typically run into with their digestate in 245.1. One is that there may be a high surface tension which will create robust bubbles. So we've designed this serpentine path with these sharp edges to help break down the bubbles before they exit the gas-liquid separator. That keeps the liquid going down the waistline and the gas free of liquid moving to the detector. Secondarily, there are problems where you may have a precipitate at the bottom of your digestate, and that can clog orifices that may be located throughout the rest of the system. And what we do with our sample probe is we actually attach a very fine mesh, Teflon mesh, to the end of the sipper probe so that it occludes any of the particulates that could end up getting into other systems and clogging it. The third thing that's a problem with some samples is that it may take a little bit longer for the kinetics to complete the reaction and reduce the mercury to vapor phase. What we have in our gas liquid separator, although it doesn't look very large, it actually holds about 10 mLs of solution. So it is actually held in the cell for a fairly decent period for reaction. And additionally, we put a fairly significant gas flow to it, so the shearing action of the carrier gases is quite effective in releasing the mercury. The last thing that I think that I would mention about our system that's unique is that we do handle overrange protection and baseline correction. These are 2 important things. That help both with stability in the baseline correction and with protection from overrange samples, unknowns that may get into the system that are high in concentration and contaminate the system, requiring long washout. We will anticipate them by looking at the rise in the signal before we take a measurement. If that rise occurs too rapidly, we know that the sample will be overrange, and we will stop the analysis, goes directly into rinse, eliminate the reading period time, and wash it out, monitoring the delay or the decay of the signal until it returns to a stable baseline. Then we'll flag that sample for dilution and move on to the next sample. It eliminates any operator or requirement to address contamination. The other side of that fast our sample cycle is that we get very good stability because we're reestablishing the baseline between every reading. We actually can look at lower limit precisions. Typically, the report limit for 245.1 is 0.2 part per billion. So that 0.2 part per billion corresponds to the lowest standard and the lowest level of mercury that operators can report, laboratories can report. And it's typically allowed 20% variation. So it can go from 0.16 to 0.24 and still be in compliance. This is actually a plot of this standard checked over an 8-hour period. And over that 8-hour period, it's varied less than 8%. So it's very stable analysis. That's a quick view of again, the drinking water approach, which does require cold vapor atomic absorption. Let's take a look at wastewater now. In wastewater, again, this is controlled by the Clean Water Act, not the Safe Drinking Water Act, and it requires methodology that is much more sensitive. From the actual Code for Federal Regulations sections, we get a table that defines what is allowed for mercury. And you can use 245.1, again, the cold vapor atomic absorption approach, or you can use two fluorescence techniques, 245.7, 1631. The difference between when you can use each of these depends on your report requirements. For 245.1, 245.2, you can only report down to 200 parts per trillion, whereas 245.7 will allow you to go down to 5 parts per trillion. 1631 will actually allow you to go to 0.5 part per trillion and less, depending on the requirements of the regulators. This was a memorandum published in 2007. We had known about method 245.7 for probably about 7 or 8 years before it was actually accepted by the EPA. And the method is allowed in conjunction with 1631, but it does have a caveat in it that it must report levels above 5 parts per trillion. The two techniques are very similar in many regards. They both use the clean hands, dirty hands approach to sampling. This method 1669. They have very similar preservation requirements, similar digestion reagents. They use same calibration algorithm, and they use similar instrumentation. In fact, most commercial suppliers of this type of instrumentation will offer both compliance with both 245.7 and 1631 methods. The key difference in the instrumentation itself is in 245.7, the mercury is generated and passed through the fluorescent cell on continuous flow. The detector is at right angles from the lamp, so it only measures the emission from the sample after it fluoresces. In the 1631 approach, what happens is that the mercury that's generated and released from the solution is collected on a gold trap for a period of time. And when that trap is heated, you get a very significant peak that is basically the sum of all of the mercury that's passed through and the gas liquid separator for a collection period. And the rest of the optics stays identical. The rest of the sample introductions is identical. And most systems will simply put a three-way valve in here so that it can go through the gold trap or bypass the gold trap, giving you functionality for 245.7. This is the criteria that's generated for water quality, and you can see that the values that are circled in green would be satisfied by method 245.7, but the values that are circled in red would only be satisfied by 1631. The other values that are not circled would be satisfied by the cold vapor atomic absorption approach. In 2005, there was a draft introduced for controlling mercury, a strategy for controlling mercury, and in the draft they basically stated that below 0.2 micrograms per liter, the analyst needs to make sure that the method is satisfactory, and in fact they have ruled that you do need one of the fluorescence techniques to satisfy the limits below 0.2. If you look at a table that's within this document, you can see that depending on the typical concentrations that they're expecting, methodology will either be 245.7, 1631, or 245.1 if the concentrations are high enough to allow that technology. So any one of the three methods may be used, but again, depending on the expected concentration of the mercury in the sample. Just a quick look at the sampling procedure. Originally, this was set up for two people. One characterized as a dirty hands person who handled all of the machinery and outside paraphernalia, and one who was a clean hands guy that only handled the inner bags and the sample itself. People have developed approaches to this where this can be done by one person, but some of the key elements of this sampling procedure are that the sample containers must be either fluoropolymer or borosilicate glass, and those containers are then double bagged in a Ziploc type bag for transport to eliminate contamination. So when you think of contamination, you have to realize the range that you're working in. In 245.1, you're up at 200 parts per trillion for your minimum report level. In 1631, the highest standard typically is only 1/2 of your report limit concentration for 245.7. So you're working several orders of magnitude lower in your concentration range, and the detection limit is 1,000 times lower for that technique. 245.7 is a little bit higher than 1631, and it is a little easier to satisfy its quality control requirements. The question becomes to many people, do they need a Class 100 clean room? And in our experience, we found that that's typically not required, but you do need to control your sources of contamination. And they are possible locations or causes of that contamination can come from reagents, including your deionized water and your argon, as well as the chemicals that you add to your samples. They can come from the analyst, both in terms of touching the sample or clothes that he wears, dust coming off the clothes he wears, dental work and concern with a lot of hair needs to be at least considered. Although in my own experience, I found that typically the analyst doesn't need to do an awful lot to isolate himself with booties and hair nets and things like that, unless he has either an illness, where he may want to wear a face mask rather than possibly coughing or sneezing near the sample, or has a lot of hair where things may get into the air from his hair. Finally, in the laboratory and in the environment itself, it does depend on the history of the location. I mean, if you have had a mercury spill in the laboratory, or if it's someplace that typically has used a technique that's high in mercury usage, then you certainly will have more difficulty satisfying the requirements, the contamination requirements. But typically you can maintain a clean bench top with some paper coverings, and perhaps put an isolation hood over the analyzer and your sample prep area to minimize the environmental contamination. And of course, the equipment itself. As I mentioned earlier, the sample collection only allows fluoropolymer containers and borosilicate glass. The equipment that touches the sample needs to be certified to be clean. That actually is part of the procedure, part of the method. But the contamination can come from sample bottles. They can come from hoses and tubes that are used to transfer your sample, gas supply lines. Certainly, we've seen older regulators that may introduce some mercury into the gas stream. The vials that are used on the sampler itself, and of course, gas liquid separator. If there's been a high sample that's run through there in the past, it can be a problem. Pipette tips. Again, transferring equipment can be a source of contamination. So many people use an enclosure. This is one that we happen to offer. It has a adjustable flow fan with a HEPA filter, and you keep a positive pressure inside the enclosure to prevent any mercury that may be floating in the air attached to dust particles from getting into the system, into your samples. One of the other things that you really should do is make sure that you clean up your reagents as best you can. There are a couple of reagents that you certainly can improve the cleanliness of. First is a rinse solution. If you're going to use a rinse station on your sampler, then one of the suggestions is to add 1 ml per liter of Stannous chloride reductant to that rinse solution and bubble it. This is called sparging, and that process will, just as it would release mercury in the normal analysis cycle, it will release mercury from your reagents. This can be done either with Stannous chloride itself for your reductant before you use it for the analysis, or with your rinse solution. And typically run 5 liters per minute of clean argon through the system. We use Teflon extension so that nothing else but Teflon or glass touches the solution, and run it for 30 minutes. We've found that quite often the deionized source that you use may be a source of contamination, especially if it's plumbed through part of the building and into the area where your samples are going to be digested or analyzed. At one location, we found that the deionized water that was coming out of the spigot, which was located probably 50 to 100 feet from the deionizer itself, was higher in mercury than the tap water, about 2.5 times as high as the tap water concentration in mercury. We put at the tap this polishing filter. It's a Bondstead ultra pure filter, part number D8911, and that dropped the contamination in the deionized water almost tenfold. So it's something worth considering. One other thing when you use fluorescence that you need to be aware of is that molecular species will quench the signal that you achieve for a given concentration of mercury. So if you have water vapor that is passed through your fluorescent cell, it will decrease the signal that you see, and it can decrease it quite significantly. For us, we try to overcome that using two-stage drying. We use a soda lime dryer, which is required by method 1631 to take out moisture, and it also does a very good job if any liquid does come out of the gas-liquid separator of capturing that before it gets into any of the other components in the system. We use that as the first stage, and then as a second stage, we use an Affion dryer, which is, in this case, required for 245.7. So we use the two dryers in tandem. An Affion dryer basically uses a semi-permeable membrane that has a hygroscopic radical attached to the polymer. You run wet gas through the inner chamber and dry gas through the outer chamber, and the moisture migrates from the wet stream into the dry stream and reduces the amount of moisture in the gas that comes out of the dryer. With the two in combination, we achieve very low levels of water reaching the detector. For 1631 and for 245.7, the procedure is quite similar. You can use a bromine monochloride oxidizer for 1631, or you can use hydrochloric acid. In 245.7, it's a hydrochloric acid that's used as a preservative. You let it sit for a period of time at room temperature, and then you pre-reduce it with hydroxylamine to remove the free bromine and chlorine from the sample. Basically, the sample turns to a slight yellow color because the bromine monochloride has a significant yellow color to it, and adding a small amount, 0.5% to each of your samples, will leave it with a yellow color while the excess bromine is present. Then when you add the hydroxylamine, it will become clear again. Run Stannous chloride as you did in the AA approaches, and you reduce the +2 mercury to ground state. You purge it with argon, collect it on a gold trap, and then although you may purge it with argon or nitrogen onto the gold trap, when you elute that mercury from the gold trap, you do need to use argon. The nitrogen, again, is a molecular species, and it will significantly quench the signal. So the difference, again, 1631, 245.7, is these two steps identified with the green font are not present. And then finally, the measurement is taken with cold vapor fluorescence. Both techniques require a specific calibration factor algorithm to be used. This one for 1631 is calibrating from 0.5 to 20 parts per trillion, and basically these are the peak area intensities that have been returned for the standards. This approach requires that you take the average blanket intensity and subtract it from each of the non-zero standards to give you a blank subtracted intensity. Then you divide that intensity by the concentration. Basically, it gives you a single point calibration for each one of these points. To determine the actual fit, you take the average calibration factor, and then you divide that number into any of your unknown intensities, and that will give you a feedback in concentration directly. The calibration factors for all of your standards have to have an RST of less than 10%. This guarantees that you have a linear fit. I'm sorry, it's recorded here as 10%. It has to be less than 15% to guarantee that you have a linear fit. And when you look at your report level, your lowest non-zero standard, it has to be within plus or minus 25% of the true value. Also required is a system blank check. That means when you take the intensity of the blank and divide it by your calibration factor, it returns a concentration of less than 0.5 ppt. This is a typical calibration curve that we would get. In this case, we've calibrated from 0 to 50 parts per trillion, and our acceptance criteria is reported on the screen. The RSD, which needed to be less than 15%, come back reading 6. The blank concentration has to be less than 0.5. It come back reading 0.196. And the recovery, which has to be for your report limit standard, has to be within plus or minus 25%. Here it came back reading 106%. So the 0.5 standard read 0.53. So we have two systems we offer. We offer an AF and an AF Gold. The difference is the gold pre-concentration capability of the mercury. If you do get the gold system, this panel is available, and a quick turn on this thumb screw allows you to remove the panel, and the gold trap it can be removed simply by rotating this thumb screw and releasing this assembly. So that's what you get with the AF Gold. If it were the AF, this would simply be a blank panel. This is what a typical peak looks like. This is actually our high standard, 100 parts per trillion standard that's been displayed here. It is a peak. It's not a plateau anymore because it is being eluted off of the gold trap. At the other end of the curve, this is a display of 3 replicates of a blank solution and 1 replicate of a 0.5 report limit standard. And as you can see, this is less than half of the report limit standard, which would mean that it would be a suitable concentration, effective concentration in the blank to continue with the analysis, to use the calibration. One thing that is of concern to many people is the original method, 1631B, was a manual method. So people would do the analysis in 2 steps. First, they would have a collection chamber, which might be in a fume hood and contain 5 or 10 of these stations. Each one, they would load their samples into, load in their stannous chloride, and they would start to bubble through the sample container. It would release the mercury, go through a dryer tube, and collect on a gold trap. And that would be done perhaps in 4, 5, 6 more locations. The reason for that is the original method called for bubbling for 20 minutes. So what would happen, and this actually is located in the wrong place, the sample collection trap, which is this one, would then be put into the analyzer one by one. You see if I've got it in the wrong place on all of these. Yeah, these should all be over to the next one, which is where the actual collection tube is. They would be brought one by one and put into the collection tube. And the system would fire that first gold trap and collect it on an analysis trap. The whole point of this was to have a single elution characteristic for the same trap. But with continuous flow systems, they all collect on the same trap anyway, so there really is very limited need for 2 traps. And that's why our first 1631 system did have 2 traps, and we found that it just was extra time with no benefit. So we've stepped back to 1 gold trap, which is allowed by the method itself. One other thing I might mention is that we do offer a compliance assistance. So if 1631 is a method that you haven't had experience with before, we will offer 2-day on-site training to evaluate your facilities and to help you with controlling the contamination that may be present at your site. Typically, there are several benefits that you should consider when you're dealing with the Hydro 2AF Gold. The first one, of course, is that it complies with 1631. It's a pretty tough QC requirement list that this method demands, and you really have to be able to meet all of the criteria before you can report any data. Secondly, it's pretty fast, 3 to 5 minutes for amalgamation. It used to take us 5 to 8 minutes, perhaps even up to 10 minutes to complete a analysis with amalgamation in our original system. By going to 1 trap, we've cut that time down to 3 to 5 minutes. So you can process samples pretty quickly with the AF Gold. And if you do it without amalgamation, it's identical to the cold vapor atomic absorption sample cycle. It'll take you 1 to 2 minutes. We offer, let me page up. We offer several service options that are fairly unique to our customers, which is our systems are designed to be modular, so we can replace a module very quickly, typically overnight. And if there are lingering problems that do require on-site service, we offer that as well. So you have a wider choice of service options. We do offer compliance assistance, which is fairly unique. One thing that I should mention is that the AF Gold, the way we do our analysis, is somewhat different in that we allow pre-screening of the samples. And by pre-screening, what we do is we actually uptake a very small portion of the sample and pass it through the system, but bypass the gold trap. This will generate a peak at the detector, and we'll look at that peak. If it's a very high sample, high in mercury, then we'll know that it shouldn't be pre-concentrated on a gold trap. That way we can eliminate a lot of contamination from the system. So that's all automatic. It takes about 28, 30 seconds to complete a pre-screen, which can keep the system quite clean for the future. Finally, because we do offer the system as a modular system, you do have the ability to add an AA module to an AF system and be able to do both drinking waters and wastewaters. So the instrumentation that we have are the Hydra AA, the Hydra AF, the AF Gold, and these three systems, they are limited to the type of analysis that you can do and the report limits that you can reach with each of the methods. If you do want to add a combination system, say to a Hydra AA, you can add the AF transition kit or the AF Gold transition kit, which would allow you to do all three methodologies. I really appreciate the time that you've shared with me, and I certainly leave it open to questions now.